Okay, so hello everyone. Good afternoon. We will continue our courses, chapter 13. And I think last time I delivered the midterm. And if you forget to return to me, please let me know. And please give me to me if you forgot to return. Okay. Or if you didn't bring today, you can bring maybe next week. Okay. Okay, before we continue the subject, maybe I will start by giving you a couple questions. Example for chapter 13.2, the derivative, and I think maybe focus on derivative first. So the exercise will be, so find the point. Oh, wait. Find the point on, this is the functions, the vector function. Okay. With interval of the t is from 0 to pi, and the tangent line is parallel to the plane yeah, this is the first one. So maybe we can start with this question first. So find the point on a vector function. To cosine t, 2 sine t, and the z is e with power of t. And the interval is from 0 to pi. And it's also mentioned that the tangent line is parallel to this plane. So what's the question asking? To find the point. To find the point. Okay. So let's see on how you solve this question. Okay. And I assure you, if you understand the questions, you will not find any difficulties in the exercise. Okay? Because typical exercise is, I think, more or less like this question. Okay? So the first thing is you need to know what the question means. Okay, so you need to find the point on the vector function, which means the vector function, it can have change in positions, right? But it needs to be when the point is where the tangent line is parallel. That's the key, the parallel. So let me underline this parallel. So you need to find the point, and the tangent line is parallel. So based on these few terms, okay, tangent line. Tangent line means you need to take the first derivative, right, out of the r. So you need to find r prime, right? You need to find r prime. And then the second one is that it should be parallel, right? Parallel means it has the same direction. So from this plane, you need to figure some direction from here, right? Usually we call in terms of n, or direction numbers from the plane. Remember in chapter 12 we have the plane equation and we have the directions number. Okay? Now we need to take from those examples. Okay, let me write the r here. R, let me rewrite the formula. So r is 2 cosine t, 2 sine t, and e with the power of t. Now let me just derive and see what's the tangents look like. This will be negative 2 sine t, right? 2 cos t, and it's the same e with the power of t. And let me give some notes here. Okay. So tangent line is parallel to the plane, right? And from here, we can also say that tangent line is orthogonal to the normal. But let me just write normal of plane, okay, to make it simple. Which means the if this is the plane, let's say this is the tangent line. Okay, let's say this is tangent. And now we have this normal. Let's say this is n. Okay? And this is orthogonal to that. This is just illustration. Okay, this is illustration for the line. Okay? So you need to be able to solve that from the questions. You need to be able to tell the tangent line is parallel to the plane, which means the tangent plane is orthogonal to its normal. Okay, and the normal we usually use the n, or we can also write down as the direction numbers, and we can find n through our plane equation, right? And from this plane here, we get that n is square root of 3, 1, and 0, right? That is our direction number from here, okay? Now, because of orthogonal, so due to orthogonal, then the r prime t dot the n should be 0, right? Or if you want to see clearly, this is because this part, and because cos pi over 2 is 0, then the whole thing is 0. So we can also say here that the dot product of these two vectors will be 0. Okay. Now we can write down all the terms, and we can just take the dot product. Now we have -2 square root of 3 sine t plus 2 cos t equals 0. Now we can solve this and find the relations between the t, right? So we have or we can simplify, become the tangent t. And because t is from 0 to pi, right, from the question, then we can just say that, okay, t is pi over 6. Now, the point that we want, this is not finished yet. The point that we want, we need to put t into the equation. So r pi over 6. So put back to the original equation. It's 2 cosine pi over 6, 2 sine pi over 6, and e with the power of pi over 6, like that. And this will be square root of 3, 1, and e. Okay. Okay. So after you get this t, don't forget to take here. And oh wait, this is the vector. We want a point, so we just need the coordinate here. Okay, sorry. Or we can say the point is okay. Okay. Any questions? Any questions? I hope you get the idea behind the questions here. Yeah. So first, it's finding the point in which it has relation with the plane. Okay. So there will be a number of variations similar to this question. It can be like parallel, orthogonal, etc., etc. Okay, let me give you another one, another variations that might be in your exercise. The curve R1 and R2 intersect each other. Just say intersect at the origin. Find the measure of acute angle between its tangent, lines um, to the both R1 and R2, which means it's actually saying that the angle is in between its tangent, okay? And the tangent is at origin, okay? This is also important. Okay, now the R1 is, let me write, tangent inverse t sine t and t squared. And R2 is t squared minus t, 2t minus 2, and ln t. Now, a few terms that you find here. Acute means less than pi over 2. Okay, 0 to pi over 2. Okay, and the question is asking the angle between the tangent. So if this is the tangent, maybe this is R1 prime and R2 prime. We have the angle here, and we need to find this angle. Okay, you can try to solve. Maybe for a few minutes you can try. Okay, so first thing is you need to derive these two, right? So first find the derive this. Okay, derive, and then you need to use the keywords origin. Okay. Origin is at this point. Okay, this is the origin. Usually it's 0, 0, 0, right? But that doesn't mean t is 0. That doesn't mean that. Okay? Because sometimes if you're not paying attention carefully, you might just replacing t with 0 because you think that will be the origin. But in this case, it's not that. So you need to find the point 0, 0, 0 through these two. Okay, so find t when it's at 0, 0, 0, right? Okay, got it? So first, let's see the R1. The first equation here, if you check with t equals 0, I think all will be 0, right? If you replace t with 0, right? The second one, if you replace with 0, it's not necessarily 0, 0, 0, right? So we need to replace with other numbers that can be 0. So we see ln here. So we will use t equal 1. And if we check to the other axis, it will also be 0. So t equal 1 will be 0, 0, and 0, right? So the first one is t equals 0. The second one is t equal 1. That will be our approach to calculate, using t equals 0 for the first equation and using t equal 1 for the second equation. Okay. So let's just maybe write the r prime first. So the first equations will be 1 plus t squared for tangent inverse. and then cosine t, and then 2t. And then let's do the second one. 2, and then ln will be 1 over t. Okay. Now at origin, as we mentioned before, so we put the first equation with 0, which means we need to change this to 0, this 0, and 0, right? So we will get the first one is 1, 1, and 0. And the second tangent, the R2 tangent, we put t equal 1. So this is 1, 2, and 1. Okay. Now we can calculate the angle from these two vectors, right? So calculate the angle through our cosine formula with the dot product, right? And if you want to find the value, maybe I can write here the value of R1 for the tangent. The first tangent is square root of 1 plus 1 is 2. The value of the second tangent is 1 plus 1 plus 4 is 6, right? Okay, got it? And then we can apply to here. So R1 prime, so 1 plus 2 plus 0, right? Divide by square root of 2 and square root of 6. So 3 divided by square root of 12, or 3 to square root of 3. Or we can simplify this, multiply by square root of 3, square root of 3. This is half square root of 3. Okay. So theta is, because it's due to acute, so theta will be pi over 6. Okay. I hope you get the idea behind all of this. Okay. So chapter 13 and 12 are really close each other because all the vectors is on chapter 12, and the vector functions, because it's using the vectors, so you might as well using some relations from the chapter 12. Okay, so that's why I'm combining chapter 12 and 13 in one quizzes. Okay, any questions before we go? Okay, if there's no questions, let me move to the 13.3, what we have done here. We already arrived at the arc length. Now let me continue from this arc length to the arc length functions. Arc length functions, okay, as in the first calculus, the calculus 1, usually we are using x, and then we are determining the arc length based on this, and then we put all the information for the formula there, right? So instead of x, because we already have t from our parametric, so let's use t, and let me write the equations first. Start from a. Actually, this is any constant here. It can be a, it can be any constant, until some t. square root of, let me use another variables here, pu. If in the first column you have t and x, right? Now you have t and u. So actually, what does it mean for these functions here? So actually, if we are trying to visualize what it looks like, let's say that's our vector functions. Let's say this is C. Okay, let's say we are start from the position A here. Let me write here. Let's say this is RA from T equal A. And then we are going to, let's say, until here. Let's say this is our RT. Okay, so RT is variables, meaning we can imagine this curve. Okay, so we can imagine this curve. Okay, this curve C. We can cut in a segments. Okay, and the segment we can move the segments. Right. So this RT we can move it to any point we want. Okay, so basically, what we are going to do is we have the arc length, right? The arc length is a constant. It's already geometric, independent of any variable. So what arc length functions means is we can make out any functions by cutting this arc length and making a new variables. So we can put more than one variables. We can put more than one functions. For example, this is A, this is T. Maybe we can put U. Okay, we can put another variables and we can include them all together and find the relations. Okay, because the arc length will be not affected by that because it's already independent by itself, right? So um, it can be we can measure or visualize if we have like a data set that has a curve. If you want to observe in certain segments, we can put some restrictions there, and we can use any functions that can approximate that line. Okay. But let's say we have this, okay, and the S here means the S. This functions means this line. Okay. So this is actually what we call by reparametrizations. Reparametrization. So maybe the first we have parameter, but we can reparameterize and using another variables to say about that function. So for example, okay, for example, let me just go for the example in a question. Okay. So example, find arc length parametrizations. Parametrization, okay, of the functions are, the functions is cos t sine tj plus t. This is the helix with reference point 100 and same orientation of helix. So meaning reparameterizations means it can be opposite directions, but it is on the same arc length. It can be. So we can reverse the arrow if you want. But here the example is I think the simple one. It's just the same as the helix. Now to deal with this question, okay, before we are looking at the vector function, we need to decide which variable we are going to use. Okay? It can be any variable you can choose. It can be v, u, any variables. For example, because your textbook using u, let's just use this as our basis. Okay, this du. Okay, so what we are going to do is we are going to imagine this whole function is in u variables. Okay, let's just write in terms of u. Okay, and let's find the tangent. So basically, the tangent is what we are looking for. This one. Okay. Now we are going to write down the s as the integrations because the reference point is at t equals 0, right? This is at t equals 0. So we can say that our a is from 0, okay? And at and we integrate until t, okay? And then put all this r prime inside. Uh, it's squared. It's squared all the r prime. So sine squared plus cos squared and plus 1. Okay, and it's du. And solve this, we get it's square root of 2 du. And we can integrate this, and we can write down this as square root of 2t. This is s. Okay. And now we can have t is actually square root of 2 over s. So we can reparameterize. Okay, so we can. So this is our new parameter. We say this is our new parameter. And we can write down a new parameter s cos s squared of 2I plus sine s squared of 2k and plus s over square root of 2k. Okay. It can be helpful. Okay, it can be helpful, especially if you are maybe finding that from maybe a complicated parameter and you want to simplify that. We can simplify the parameter with this method. We can reparameterize. Okay? Reparameterize. So we can reparameterize, and oh yeah, I forgot something here. So notes, if I write this as, let me write first here. Okay, we can write this as integrations of, this is the r prime, okay? The value of r prime. And du. Or we can write this, if we derive the arc length functions, we get the r prime, the, right? This is fundamental theory of calculus. And this part is, I think, helpful, especially if you are going to deal with vectors in your next courses. Because I think if you are dealing with like a mechanical property, like how torsion works, yeah, torsion and how the vectors looks like, you need to understand the concept in chapter 12 and 13. Okay, that's the arc length function. So the idea is to reparameterize the new parameter. Okay. Okay. Now from here, let's go to what we call the curvature. Okay, the curvature. Okay. The symbols is like this. Let me write something first. We call the parameterizations, as we did before, is smooth on some interval, let's say interval I, if the r prime is continuous and the r prime is not equal 0 on the interval I. Now we have a new terms also, it's smoothness. Okay? So smooth, what does it mean? So smooth is, if you look uh, at the line or curve, maybe your curve like this, and the other one's like this. Of course, you can always tell that the right one is, the smoothness is higher, right, than the left one. Okay. Now, if we are having, let's say we have just have this 2-dimension x and y. Okay. Let's say we have this from point A. This is B and this is C. Okay. Now let's look at some tangent vector on each point if we take A to B. Okay. If we are going to observe A, B, okay. Let's see if the first A is like that, for example, the tangent. And the second is like that. And the third is like that. Okay. So the tangent is it's changing, okay, but it's still at this directions, right? Not really that extreme, right? So it's just like, okay, it's changing, it's changing, it's changing, okay? Now look at B to C. Okay, from B is going here, and then here, and then here, and then here, and then here. Look at how fast it's changing. How fast it's changed, that's the curvature. Okay, you get it? Okay, from the picture. So if you compare this from A to B, it's not too extreme, the change. Okay, it's just okay, change, 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 right? But here it's rapidly bending, it's twist, and it's going to be really fast. The change is really fast compared to AB. It's slow, right? It's slow. Okay, so we can also say the curvature is how rapid the curve is changing. And by changing, we need to be able to calculate or evaluate. Okay, let's say from here we can take our tangent vector t, right? And from what we did previously, we know that this is r prime, right? Okay. Now let's go to the curvature here, and let me write the general equations. Okay, the general equations from the general definitions. The general equation of the curvature, based on what we have in our definition on how rapid the curve is changing with respect to the length, actually. Okay, like you see, it's still like this, but then changing to here, right? Okay, so general equations. It's the tangent vector changing with respect to the arc length. Okay, and we can break down this formula. Okay, so first, let's write this in terms of chain rule. Okay, so we can apply this chain rule, and this is the results. Okay, so we can write down this in terms of dt over dt over ds over dt. Okay, and then this is actually t prime, right? And ds over dt is the r prime t, right? Okay. it's actually having a value here. So we can write the curvature in terms of the unit tangent vector and the r prime, the tangent. Okay, let me move to the right side here. Another theorem, I think I will show you how to deal with this. So the curvature is okay. This is cross. Okay, now it's a little bit long, but I need to try my best to show you how it's done. So this is from, so let me write all the terms that we need. R prime is ds over dt. Okay. Now, first we arrange this and make it into this form. Okay. Arrange this form. And this is changing to here. So r prime is t ds dt. Okay. Okay. Now, what we are going to do, we need to find the r double prime or the second derivative. So this is, let me write t ds dt, or maybe I write ds dt first, maybe much more clear. Okay. Find the second derivative. So first is t plus ds over dt, t prime, right? Okay. So we have now r double prime and r prime. Okay. The next step is let's try to cross the r prime cross the r double prime. What we are going to do, let's write the r prime. Let's write just the SDT first. Okay. And then cross this whole thing here. If you see in your textbook, there is some mentioning about this formula, but the book didn't prove anything. They just skipped some process there. So let me try to prove the whole thing. Okay, cross this. So first cross with this, and then cross with this, right? can write ds over dt, and then d squared as dt squared, and then write t cross t, right? And then plus ds over dt. Let me make it squared because it's multiplied each other, and then multiply with t cross t prime. Okay. Okay. Now these terms, no, actually these terms will be 0 because it's orthogonal. Maybe I'm using the different color to see. So this whole unit tangent vector is 1, right? And the we need to prove this to be, or maybe writing like in terms of t dot t is 1, and we can say we have this is 0, which means that it's orthogonal, and orthogonal, it's of course it's 0. Okay. Now we convert back ds over dt to r prime. So this will be r prime. R prime squared, and we have the cross is using the sign. Okay, and because it's orthogonal, we can write down into this form, and then sine pi over 2 is 1, so you can just write that. Maybe I'll write a bit below here, and write the left part is the r1 and r double prime, or r double prime r1, or r1, sorry. Okay. Now t prime is r1 r double prime, and then having the r prime squared. Okay. Now the curvature is r prime divided by r t prime divided by r prime. So we need just to divide one more time with r prime. So we have r prime cross divided by r prime cube. Now this is the proof for the whole formula. So curvature is r prime cross R double prime. And then you have R prime cube. So especially this curvature, I think the one with this formula, it's, I think, easier to apply. Easier to apply. But the calculation will be a little bit longer, but it's easier to apply for most of curvature problem. Okay. You need also to remember that this value means you need to square root and plus all the squared inside, right? And then if it has cubic, then you need to apply cubic there. Okay. And don't forget to how to calculate cross. Okay. Cross using I, J, K, and then this is insert your value and calculate. Okay. Okay. There is also another case for the curvature. So if you have a plane curve with uh, equations y equal f of x, okay? And because of this, we choose this x as the parameter, right? Now we can write down in terms of vector functions, but in terms of x as parameter. We can also write this as it's x and then I, and plus the f of x and then j. And from here, we can make the first derivative. So this is 1. So it's just I plus f prime x j. Okay. And then r double prime is basically just f double prime x at the y-axis j. And then remember that I cross j is k, right? And j cross j is 0. So if we cross these two, so if we cross this r1 cross r double prime there, so j cross j is 0, and I cross j will be k. So it will be f double prime x and then k, right? And we also have the r prime is square root of all of this. So 1 square plus f prime x. Oh, let me use different bracket squared. Now we can write down the new formula for the curvature in terms of x for the plane curve y equal f of x. Okay. And then the top one here is x. It should be cube, but let me change this into 3/2. Okay. 3/2 is from here, from this cube here. So this squared and then cube, so it becomes 3/2. Okay. So this is the case if the plane curve is functions of x or any functions that has relations for like a Cartesian. So we can also use the curvature in just the 2 dimensions term x and y. So with this approach. So for example, right? Okay, let me go here and write the example for the curvature. So find curvature. So what the question means here is if you have just y equal function of x, that means we can use the curvature formula for only this f of x, okay, like this formula here. So first is we can have the relations here. This is x squared, so we can find the first derivative and second derivative. Okay, and then we can just use the curvature formula. So this is 2. Okay, now we can look at 0, 1, and 2 for our x. So plug in 0 is 2, right? It's only 1, yeah, 2 divided by 1, 2. And for curvature 1 is for 2, 5. For 2 is 17. Okay, if you check with the calculator, this will be 0.03 and this will be 0.18. And if you plot the graph, okay, if you plot the graph, you will find so if this is okay, if this is the x squared, now we can also draw the curvature curve, how the curvature changing. Okay, so here is maybe here's okay. The red line is the curvature of x. So if you see here, the stationary point here is when the gradient's changing, right? And by our evaluation here, it's the highest point, which means it's the measure is changed really fast from this to this. And at 0, it's the point of the changing, okay? So here is the 2, the curvature of 2, curvature of 0, 2, right? So you can visualize how the curvature is at any point of this x. Okay, I think this way will help you to, I think, also to understand what the curvature really means. Okay, if you maybe difficult to understand through this all this formula here, like this, or maybe here, but basically the first definition is the curvature, how rapid or how fast the curve is changing with respect to its length, the arc length. Okay? So the first equation is the tangent vector, the change in tangent vector, the rate of change of the tangent vector with respect the length, okay, the change of length. And we have at least one, so 1, 2, 3, or this is 3, and 4. 4 relations related to the curvature, okay? And how we are going to use it? First, if you have only the vector functions and you want to know the curvature at some point, you can directly use this. Okay, it's it's just using the r prime, r double prime, and divide by r prime cube. Okay, but if you have the plane curve and you are seeing these relations, just regular Cartesian y equal f of x. If you want to measure the curvature, then you can go to here. Okay, and as we discussed before, we can see that this is actually how the visualizations of the curvature. Okay. 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 The next one is still related to the tangent vector. It's called normal and binormal vectors. And this will be started to getting a little bit complicated. So normal. Let's start from normal vectors. Okay, first, let's start by the unit tangent vector. Let's just review. This is t, right? This is r prime. Okay, this is as we discussed before. And this means it's pointing the direction of increasing parameter t. Yeah, this is just showing that if you have this, then this is the t. It's pointing the direction of the, if you increase the t, okay? It's showing you that. That's unit tangent vector. Now you have unit normal vector. Let me write the formula first. The formula is the tangent prime divided by the value, its value. Now, how we can visualize? Let me write some words here. So it's pointing inward towards concave part of curve C. Okay. What does it mean? Okay, maybe this will help you better. If you have this, let's say this is C, and this is the direction. Okay. Now, uh, if you have this is the T, normal vector is here. That's what it means. So it's pointing back to, so if you have the concave is here, the normal vector is always going here. Okay. If the tangent here, then this will be the normal vector. And this is orthogonal. Okay. To make it more interesting, the other one is called binormal. The definition of binormal is binormal vector is orthogonal to tangent and to normal. So it's probably here. Okay, got it? So if, let me maybe make it like this. If this is tangent and maybe this is the normal, then this is the, usually we using B for binormal. So this is, but maybe right. So binormal vectors means it is orthogonal to normal, and it's also orthogonal to the tangent. Okay, so binormal vector is orthogonal, or maybe if you more familiar with perpendicular to both T and N. So how we are related B, T, and N? We can relate it through the cross, okay, cross product. So T cross N is B, right? Okay, because it's all factors. So let me write here. T cross N. Okay, maybe some example first, and then maybe a little bit last part, and or maybe just example, and then we can finish. Okay. Okay, so let me review a little bit. So first, maybe this is normal and binormal. So first, remember you have unit tangent vector t, okay, this t. And to find the normal from this tangent vector, we need to find the orthogonality from t, okay? In which if you have curve C, it will point inward here, okay? Or you just write here and then take orthogonal here, okay? And then we have also B, we call the binormal vector. The binormal vector is orthogonal to T and also normal vector. So we have this. And from what we have discussed before previously in chapter 12, when we want to have uh, a vector that perpendicular to both vectors, we need to use the cross product. So we can use cross product here to define our binormal. Okay, so that's normal and binormal. Okay, let's move to some examples. Maybe move here. Okay, so example. Okay, we need just to find the unit normal and binormal vectors. Or circular helix. The equations is the helix circular is just the same as we did, cos and then sine and then just t. Okay, what we are going to do, we just need to find the unit tangent vector first from r prime. And calculate the value. And we have the unit tangent vector is, let me write this, and divide by this. And we have, or maybe to make it more clear, and then we find the t prime. So derive once more. Oh, minus, sorry. 0, yeah. Stop here. Find the value. It's just 1, and it's just 1 of square root of 2. The normal will be t prime divided by if you see, it's just dividing the 1 over square root of 2, so it will be like this, cos t I minus sine tj. That's our normal. Or you can write in this way. It's also the same. And then the binormal is crossing the T and the normal. Now, because T, we have a constant 1 over square root of 2 and N yeah, we can write the we can factorize first here and write the I, J, K. T is, what is the negative sign? And to solve the cross, it's up to you which method you want to use. Okay, you can use the determinants. Okay, you can use the. Usually, I'm using this. So I'm writing another I, J, and then write another sign. And then this is too close. Maybe you will confuse a little bit up here. So this multiply plus this multiply and also plus this and multiply minus this multiply minus also this and minus this. Or you can using determinant, it's also fine. Then you will have negative cos t for j, and then cos square t plus sin square t for k, so it's 1. And then minus sign, so it's positive sign for I. So I will get sin t negative cos t and 1. Okay. Okay, maybe another example, and then we can finish today's class. Okay. Okay, I hope you familiar with the cross product. Okay, so if it is in maybe in the quiz, I hope you can finish it. Okay, you can solve the cross. Another example. Find unit tangent, unit normal, and binormal. And curvature. For curve R, T square root of 2L and T 1 over T at 0.101. Okay, basically what what we are looking for is we need to start from the first derivative and finding t, finding n, finding b, right? And then we can find the curvature with the t prime and r prime. And then basically we are already 90% finishing the chapter 13. Next Tuesday, I will finish the chapter 13 and move to 14. And probably maybe 27, 27 of May, quiz for 12 and 13. And I hope before that we can have some practice. Okay, let me also write for you some part, maybe if I have the time. Let me write the r prime from this is 1, and then square root of 2 over t, and then 1 over t is negative 1 over t squared, right? And then the value for the magnitude is 1 plus 2 over t squared plus 1 over t4. So we get 1 over t squared t4 plus 2t squared plus 1. This is yeah. So we can have t squared plus 1. Now this is, it's not positive negative because took positive because t squared plus 1 is always positive, right? So unit tangent factor is r prime divided by the magnitude of r prime. This is the magnitude, and then the factor r prime is, I forgot which, 1, and the square root of 2t and negative 1 over t squared. And we can simplify, become t squared plus, okay, now this is t. Oh, I think it's quite long, right? Okay, now we need to use the product rule. This fg. So first is find the derivative of this. So this should be squared here, right? 2t, negative 2t. And this is the same. And plus the other product rule. This is the same. And this will be 2t, square root of 2 and 0. Right? Any mistake here? No, right? Okay. The magnitude of t prime. Oh, wait. Before that, let me check the questions. I forgot. Oh, the point is 101. So point. So let's here. So at we need to check the R. The R. So if we check this 1 over t, so t should be 1, right? If t1 check the other one, this should be 0. It's correct. And the other one is 1. So t equal 1. Okay. So at t equal 1. So this is t equal 1. Okay. Okay. We can simplify all these equations and putting 1 inside all formula. So it will be t is what? T. So half 1, okay. 1 square root of 2 and negative 1. And then this prime. Negative 2 to 4 for negative half. 1, oh, it's the same. And plus half 2. Okay. Okay, now it's better finding the n. Oh, we can solve this. Half 1 negative. Oh, this is back to, oh, yeah. Okay, so half 1, and this is the square root. Okay, and the rest is crossing this, crossing the t and n at 1. So you can use this t and crossing this n. Okay. Yeah, I think you can do that by yourself. Okay. Okay. Oh, one more is the curvature at t equal 1. So we can use the t prime at 1 and r prime at 1. You can compute that also. And I think I will leave the rest to you. So as long as you are familiar with the vectors, how to compute okay, the dot product, the cross product, and also understand the definition of the new terms you have, okay, the curvature, the normal, binormal vectors. I think it should be fine, okay. What you need to do is just try to apply in some exercise, okay, in some cases problems, okay. I think in the last year midterm or quiz that I give you, there are several questions related to vectors, and you can try to check. And try to check. Okay, next week we will start at the last part of the chapter 13 and move to chapter 14. Okay, and remember, probably the quiz will be next 2 weeks. Okay, so 27. Okay. 27. The chapters will be chapter 12, the vectors and vector functions. Okay. And the question will be probably like, it will be like combination of those two. Okay. And I will also give you maybe the exercise on the textbook, the PDF file, to help you practice. Okay, any questions? If no, I will stop here and